Thank you. Welcome back from lunch. My name is Craig Hardgrove. I'm a professor at Arizona State University. Um, I am a co-investigator and instrument scientist on lunar-VISE, which you heard about yesterday from the PI, Carrie Donaldson-Hanna. Um, and I'm also the instrument scientist for the gamma ray and neutron detector. I'm going to tell you a little bit about how the instrument came together and some of the science that we'll be doing on the mission. For those of you that aren't familiar with neutron and gamma ray instruments, you may have seen this map of the south pole of the moon. This was made with Lunar Prospector's neutron detector. The red shows hydrogen enrichments. And you can see that there are some broad patterns. The spatial resolution of this map is fairly coarse. We're thinking somewhere around 30 to 50 kilometers per pixel. So from orbit, these measurements incorporate a lot of ground. You may also be familiar with this map. This was made with Lunar Prospector's gamma ray detector. And on the left, you can see a map of thorium on the near side and far side. You can actually see the enrichment that lights up near gruithuisen domes. And you can also make fun maps of other elements with gamma ray detectors, iron, titanium, magnesium. And so I just wanted to point this out again to say the spatial resolution of these is quite broad. And so Carrie did a great job of explaining why we want to go to gruithuisen domes. These are these potentially high silica materials that may be enriched in thorium from these orbital measurements, but we really don't have a good sense because of the broad spatial resolution for what these materials are made of and how they might have formed. So we want to go to the surface and make surface measurements to really understand the formation of these high silica volcanic features on the moon. So this is one of two slides on nuclear spectroscopy, just to familiarize you. The signal comes from cosmic rays. That's what these guys are up there. Coming down, these are high energy protons, and they interact in the subsurface. They bounce around in nuclei in the lunar regolith, and they generate high energy neutrons. And those high energy neutrons bounce around, and they generate characteristic gamma rays that tell you about the elemental composition of the surface. They also lose energy. Those neutrons will lose energy. And if there's more hydrogen in the ground, they lose much more energy. And so if you see a lot of low energy neutrons leaking out of the soil, it'll tell you that there's more hydrated material in the ground. Also, from elements like potassium, thorium, and uranium, those are naturally emitting radiation, so we can detect their characteristic gamma rays without using the cosmic ray background. And this is just a little sketch to show you all the different nuclear interactions that happen and the elements that we're sensitive to with these types of measurements. These are pretty popular instruments throughout history of planetary exploration. I brought this up just to show you that there are a few that I'm going to bring up that sort of led to the inspiration for the lunar-VISE gamma ray neutron detector. One is the Curiosity rover, which is shown in the upper right. That carries a neutron detector that while Curiosity is driving around on the surface, we're actually interpreting the neutron signals from what's underneath the back two wheels. So as opposed to looking at orbital maps that are many tens of kilometers wide, we're thinking about rock compositions that are right underneath the rover. That's going to be very relevant for what we're doing on lunar-VISE. And then another mission is LunaMap, a mission that is near and dear to my heart. I was the PI. It launched, you heard from Lori Glaze yesterday, as one of the CubeSats that launched on SLS with the first launch. We were lucky enough to collect some data on our lunar flyby, which I'll show you later. And we used a version of the instrument that will be flying on lunar-VISE. Okay, so I want to show you a little bit about LunaMap since this is my third child. It's a 6U CubeSat, about 14 kilograms. And to execute this mission, we had to develop a new type of neutron and gamma ray detector. That's because we wanted the front face of the CubeSat to be lined with neutron-sensitive material. We wanted it to be very efficient. So this is a material that's called CLYC. It's an El Paso light scintillator. These materials create a light flash when a neutron or a gamma ray interacts, and you connect a photomultiplier tube into a readout system. And you can generate plots that look like the one in the left bottom there, where you actually separate that bottom blob is the neutron signal, and the thing on the top is the gamma ray signal. And this is very unique for what's ever been done before in planetary neutron spectroscopy. You usually have two detectors for these types of things. So we weren't actually interested for this mission in both the gamma ray and the neutron signal. We really just wanted the neutron signal, and we were using this to eliminate backgrounds and to make sure we had a really clean signal. And this is some of the data that we got. So we were deployed from SLS, and we took a ballistic flyby of the moon around the equator. And the dark points are the points where we collected data, just under 4 hours of data on our equatorial flyby. And this is some of the data that we collected from just one of our sensors. We actually used an array of 8 sensors. And you can see there at close approach, the little neutron blob that I pointed out lights up. And so we were able to see in neutron eyes the moon sort of come into view and fade away. And we'll be able to make a map. It's not the map that we hoped for with LunaMap, obviously. We were hoping to map the South Pole and the water distributions. But we will be able to make a broad spatial scale map and demonstrate that the instrument worked quite well. So that's the end of the LunaMap story for this talk. And I want to move on to just briefly Mars, because this is very important for what we're going to do on lunar-VISE. This is the first time we've brought one of these nuclear detectors to the surface of another planet on purpose. And so there's a story about the NEAR mission there. But on Curiosity, we did it on purpose, and we drive around, like I said, and we make these measurements at the end of every stop and along drives. And so one of the really great things that we're able to do is use the instrument's field of view to determine what rocks and materials we're actually sensitive to. And we can use those to reduce the number of variables that we are needing to model and understand what the neutron signal is telling us. So we have a lot of commensurate measurement or coincident measurements with infrared spectrometers, APXS, and other data sets from the rover that we can use to really get a handle on what the nuclear data sets are telling us. So that red circle there is our field of view. Again, it's really just shrinking everything down from the orbital perspective. And these are just some of the highlights from what we're able to accomplish with the neutron detector on Curiosity. We see changes in composition on the hematite ridge feature on the left there. We see changes in diagenetic features like what you see in the middle. This is a hydrated, called a fracture halo, so water, highly acidic fluid sort of percolated up through the surface. And we see there's this bleached rocks, and we were able to see these really well with the neutron detector. And the one on the right doesn't look all that spectacular, but we were actually able to see below the surface. So neutron instruments and gamma ray detectors are sensitive to up to 1 meter below the surface. So we're collecting neutrons and gamma rays from those depths. And so we were able to test a hypothesis that the team had, that there was actually a buried layer of very silica-enriched material. We were able to show that that extended about 10, 15 centimeters below the surface throughout that region that's shown on the right. So again, using the sort of unique capabilities of the instrument on the surface. And another unique capability that we're demonstrating on Curiosity is sensitivity to nearby topography, which is going to be very important. So Carrie mentioned that we want to be able to drive up to boulders and make measurements of potentially the thorium content. And so we're able to demonstrate with Curiosity that as we drive close to nearby walls of terrain, that we actually see a signal from those in the neutron detectors themselves. It actually contributes to our signal, and that signal is reflected in the composition, right? So that we can actually tell something about the composition from that. And so there's some work that we've done there. And so, okay, so I'm going to talk about a little bit. The rest of the talk is just about what we can do with the lunar-VISE gamma ray neutron detector. This is a CAD. As Carrie mentioned, we passed CDR in January, but we have 2 sensors. One's larger. It's wrapped in gadolinium. It's going to be sensitive to gamma rays primarily, although it will also collect neutron data. The other one will be wrapped in, this will be bare, wrapped in tin, and it will be sensitive primarily to neutrons. And that's an example of some model spectra on the bottom left. The whole instrument itself is less than 5 kilograms, uses less than 6 watts. And so we get a pretty good energy resolution, about less than 5% at 662 keV, which is just around where Lunar Prospector was as well. So equivalent. These are some of the spectra that we would collect. These are simulated spectra with noise added. This is what we would see in a 30-minute measurement. You can see that the thorium peak sticks out really nicely. That's one of the primary science goals for lunar-VISE, is to detect the thorium. In this simulation, we can also see potassium and uranium. And if we are fortunate enough to be able to stop for longer, we can reduce the noise with a 4-hour measurement and still see the peak. So we should be able to use the instrument while driving as well as at dedicated stops to see the elemental composition throughout the gruithuisen domes. This is a plot just to show our sensitivity to thorium. We used a whole bunch of lunar compositions and simulated a variety of thorium contents just to show how that change in peak height varies with change in thorium abundance. And it looks like we'll be able to constrain thorium to, our requirement was plus or minus 5 parts per million, but as you can see in the plot on the right, it looks like we should be able to get closer to 2 parts per million or so, which is great. We're also, as I mentioned, sensitive to neutrons. So we're looking at, again, a variety of compositions of the lunar surface and looking at the thermal and epithermal neutron signals and showing that we have really good sensitivity to those with varying hydration. And this just shows how well we can reconstruct what's called the macroscopic neutron absorption cross-section, which is a mouthful, but it's really a proxy for the amount of iron in the soil. So it's a really great way to confirm, or at least help confirm the findings from the infrared spectrometer. Okay, so we did some testing. This is fresh off the press, not even off the press, this is fresh from the test bed. Last week, we went over to UC Berkeley and took just a prototype detector. This isn't flight hardware. This is just something we have in the lab. It's a smaller sensor than what we're using on lunar-VISE, but they have a really great facility there where we used the neutron source that they have to actually irradiate the sample. It's not the same energy as cosmic rays. It's much lower, but it's something that's very high flux and simulates the neutron environment that we'll be experiencing. And we were actually able to use lunar regolith simulant, different amounts of polyethylene underneath the lunar regolith simulant, and radiation sources as well. So we were able to embed thorium inside the regolith to see how well we were able to see that. And so this was a interesting and fun test that we were just able to do. These are some of the compositions of the soil. And we're still in the process of going through all the data because this is just fresh from basically last week. But I did want to show we did see some good results. The blue line that you see on the left is the spectrum from CLIC. This is a sensor, again, smaller than what we'll see with lunar-VISE, with the thorium and a sodium-22 source very close to the sensor. And that's what all those wiggles are. The 2.6 MeV peak that's labeled is thorium. And then the black and the red spectra, which don't look too different from the zoomed out view, have the Mare soil simulant. Again, I know that's not as relevant to the gruithuisen domes, but we did use a Highland simulant as well. We just haven't finished processing the data there. But we have both for the Mare simulant and then the Mare simulant with the thorium embedded. You can see on the right that we do actually see a little peak. And I just want to point out here that it's just a little packet of thorium. It's not uniformly distributed throughout the soil. So it's understood here that we wouldn't be seeing a very strong signal from the thorium. We really need to get it embedded throughout the soil. But it did show that we do see a signal from it in this sort of lab setup. So I think that's my last slide. I just wanted to say we're really happy to be on this program, continuing some of the work that we did on our tiny CubeSat and really pushing the capabilities of this type of sensor. And it wouldn't be a instrument talk if I didn't show some flight hardware. Those are our flight voltage dividers that just came in May. So thank you.
Thank you. Thanks for the presentation. It's just on time, so you might have 1 or 2 questions there.
Hello, thank you for your talk. I had a question about the detector. So how are you using the gamma ray detector to clean up signal from the neutron detector?
Yeah, so it effectively removes the background. So we were able to see, like, if you just had the gamma ray spectrum that I showed, and we have a neutron peak in there. So we're actually able to separate out that gamma ray continuum from that peak. So we're able to separate the background of the gamma rays that are inside the instrument's detection capability itself. So you use the shape of the pulse to separate those out. We still do see background from the spacecraft. In the case of LunaMap, our spacecraft was 14 kilograms, so we expected to see less than 1 count a second from our spacecraft.
One more questions? Anyone has? Maybe I can ask one question. I'm just novice, so I'm just wondering what kind of scientific activity we can investigate with these types of data.
Yes, I think, like I mentioned with Curiosity, lunar-VISE has a suite of instruments. And one of the great things about having a nuclear instrument in combination with cameras as well as infrared instruments and other data sets is that you can constrain the models. So we get, I mean, what I showed you there as counts or a spectrum, but we really have to model that to understand what's happening in the subsurface. So the more surface measurements we can get of temperature, composition, it really helps us understand what's going on in the subsurface with the hydration, and in this case, the thorium content and other elements that we might be sensitive to. But a lot of the gamma ray measurements that I showed are going to be sensitive down to 15, 20, 25 centimeters, where most of our instruments aren't going to be able to see. So this is really our shallow subsurface probe, and we need as many constraints as we can get. So I think it's really ideal to be on a rover, this type of mission.
Thank you.